This is problem 10-3. For part A, you have to use Ampere law to determine the magnitude of the magnetic field at a distance r from the axis. In the first part, your radius is between 0 and A, so it will be somewhere inside the central cylinder. So it will be something like this. So here's Ampere law. The cylinder have uniform current, so you can calculate your I enclosed. The I enclosed is equal to your current density your current per unit area of the cylinder, so pi a square, and times, so this is your current density, and you times it by the circle the cylinder you're gonna make with the radius r, so pi r squared. So your I enclosed turn out to be I r squared over a squared. Now going back to Ampere's law, so B dot dl is equal to mu naught I r squared over a squared. dl is equal to 2 pi r, and you divide each side by 2 pi r, so your magnetic field is equal to mu naught I over 2 pi mu naught I r over 2 pi a squared. Okay, so that's how you do part 1. And for part 2, your radius is now between A and B. Your I enclosed this time is only the current within the central cylinder, so I enclosed is equal to I. So this time is much easier to do. So again, B dot 2 pi r is equal to mu naught I. So divide both sides by 2 pi r. Magnetic field is equal to mu naught I over 2 pi r. Okay, now for B. B asks you when r becomes greater than when r is greater than c. So the field is equal to 0 because, well, you have current going in opposite direction, so the net current is equal to 0. So okay, so for part C, you have to draw a graph of the magnetic field as a function of the radius. So we've learned that from part A, from 0 to A, the magnetic field is equal to mu naught I r over 2 pi a squared. So that means that the magnetic field increases at a rate proportional to the radius. That means it should be a straight line from 0 to A, increasing. Okay, so from B to from no, not from B to from A to B, we also figure out from part A that the magnetic field is equal to mu naught I over 2 pi r. So this time, we know that the magnetic field is decreasing because the radius is increasing, and it should decrease at a rate proportional to 1 over r. So it should be a curved line. Now from B to C, the line continues to decrease, but this time at a steeper rate because the I net enclosed is decreasing and the radius is increasing, so an even steeper line. Now from B we figure out that from part B we figure out that when the radius is greater than C, the magnetic field is equal to 0, so it's just 0. Okay, and lastly for part D asks for the magnitude of force on the charge Q at P. So on the picture, P is right over here. So the force of magnetic field is equal to QV cross B. Now P is a point between A and B, so we can use the magnetic field equation we've got from part A, the second part of part A. So B is equal to mu naught I over 2 pi r. So we just substitute that in, so force is equal to mu naught I Q v over 2 pi r. Okay, for the second part of D, you have to determine the direction of the force exerted by the magnetic field on the point charge P. So we know that the current is pointing out of the page on the inner cylinder, and by using the right hand rule we can figure out that the magnetic field is going in a counterclockwise direction. So at point P, the magnetic field should point straight up, and the question said that point P is a positive charge with velocity going directly out of the page. So it's out of the page, and by using the right hand rule we can see that the force is pointing directly to the left. And lastly, for part E, the current in the outer cylinder shell is reversed, and now both currents are going the same way, and they're asking what effect would this have on the answer on part D. And there shouldn't be any effect because the Ampere law is integral of B dot dl is equal to mu naught I. Whether or not there's current on the outer cylinder shell doesn't affect the magnetic field, because the I here is only the current enclosed. So unless the current of the center cylinder changes, then the field stays the same no matter what happens to the outer cylinder shells.